Good evening, everybody, and welcome to this public lecture. Before I say something about the ICTS, the inaugural event, I'd like to invite Mustansir Barma, the TIFR Director, to say a few words.
Thank you, Spencer. It's a great pleasure to welcome all of you to this first public lecture during this inaugural function of the ICTS. I just wanted to say that public lectures are very much part of the ongoing effort at TIFR, ongoing outreach effort at TIFR, and I think therefore it's only appropriate that this new of the institute, namely ICTS, also establishes a tradition of this sort. Indeed, the ICTS mandate includes, quite importantly, science communication, and this series of public lectures, I'm sure, will be an important part of this process, because there's no better way to convey the excitement of science to the public at large than to have the practitioners of science, who themselves are involved in redefining the frontiers, actually talk about it. For us at the Tata Institute, this has been a especially significant year. It's the birth centenary of Dr. Homi Bhabha, the founder of our institute. But in fact, the vision of Dr. Bhabha was first conceived in the corridors of the Indian Institute of Science here in Bangalore. Therefore, it's really quite appropriate that this first ICTS public lecture is being held here in this auditorium named after J.N. Tata, because included amongst the many things we share in common, by we I mean the Tata Institute of Fundamental Research and the Indian Institute of Science, is an involvement with the House of Tatas in different ways. And therefore, I think it's very nice that this lecture is being held here, because it once again underscores the strong links that exist between the two Tata institutes. Thank you.
Thank you, Mustansir. I'd like to say a few words about the International Center for Theoretical Sciences. It's a new center of the Tata Institute of Fundamental Research. It has a few primary goals. One of them is to enhance the quality and level of research in India. So in that sense, it's an institution or a center for the whole country. And we're very fortunate actually that the government of the state of Karnataka has given us very prime and pristine land actually in North Bangalore for the construction of this center. Besides the research enhancement, I think one of the important things the center wants to do is to create a gradient for young people in science to come and see what the beauty of the world around us actually, and how it functions in various different layers. And therefore actually we have planned in the next few days some sort of a science festival actually, in which there are internationally renowned people in areas from physics to chemistry to biology to mathematics to computer science, across the board, but sort of trying to tell each other and all of us the the melting of the various boundaries of science. So I would like to invite you all actually, to this Festival of Science in the next few days, starting from tomorrow morning. And we also have, at the end of most of the days, public lectures. So this is the first public lecture. The second public lecture will be tomorrow in the same auditorium at the same time by David Krauss on the importance of theory in science. And then on Wednesday, in the same auditorium at the same time, we will have Albert Lipscheber telling us about the origins of life. So you can now imagine the expanse of our enterprise. So we'll say more things about our center in the next few days. But before I leave this, before I end my small presentation, I'd like to say a few words. The original speaker for this public lecture was Professor Michael Atiyah, very renowned and well-known mathematician. Unfortunately, he was taken ill a few days ago, and therefore he had to cancel his visit. So in fact, I had invited Professor Jayakumar Radhakrishnan of the Tata Institute's Computer Science Center to my office to discuss what more we can do with AVI Wigderson, actually, in the days that we are here, and to discuss with him. And I saw this email from Atiyah, and it immediately occurred to me that it would be wonderful if AVI Wigderson would actually give this lecture. And it happened so naturally, so smoothly, right away. He was vacationing in the south of India. And in fact, both Avi and Jayakumar have cut short their vacation in Karnataka, in Hampi, and have come here for this lecture. So I really would like to take this opportunity to thank them for doing this at such short notice and so easily, actually. Okay, thank you. So I'd like to now make some presentations. So, and also to Jayakumar. Oh, it's also for you. I think something else is coming also. Now I'd like to invite Professor Jayakumar Radhakrishnan to introduce AVI Wigderson.
Dear friends, we hope Professor Atiyah recovers soon. Our speaker today is Professor AVI Wigderson. We are very happy to have him here. Professor Wigderson has been perhaps the most influential computational complexity theorist in the past more than 2 decades. He's the author of landmark works in areas such as interactive proofs, zero-knowledge proof systems, cryptography, proof complexity, circuit complexity, communication complexity, lower bounds, and de-randomization. His works, especially those on the relationship between randomness and computation, have time and again revealed deep and surprising connections between various areas of computer science and other areas of mathematics. Professor Wigderson obtained his bachelor's degree from Technion Haifa, Israel in 1980, and his PhD from Princeton University, USA in 1983. He has held academic positions at several leading universities in Israel and the United States. He is at present the Herbert Maas Professor at the School of Mathematics of the Institute for Advanced Study, Princeton. Professor Wigderson is the recipient of numerous awards, including the Nevanlinna Prize, and the Gödel Prize. As I invite you to listen to Professor Wigderson's talk, I recognize that perhaps a majority of the members of the audience work in areas somewhat removed from computer science. I must, therefore, invite you to another of Professor Wigderson's talks. He has on his homepage a talk on why we must listen to talks in other areas. Professor Wigderson represents that creed of depth through breadth. Ladies and gentlemen, please switch off your mobile phones and welcome Professor AVI Wigderson.
Thanks a lot. Thanks for inviting me here and to give this lecture. I too hope that Professor Attia will recover quickly. I want to tell you about this P versus NP problem, and my title, which I have to make good with, is Efficient Computation, Internet Security, and the Limits of Human Knowledge. I have to show you what's the connection of this mathematical problem to these, other words that appear then in yellow. So you might have heard of this problem because it has $1 million prize on its head. It's one of the 7 Clay Math Institute Millennium problems that are listed there. Each has $1 million prize on it. Actually, if you want to participate in this competition, you should know that one of them is already solved, so you should maybe hurry. What I want to invite you is actually to think about and maybe work on the P versus NP problem. Now, this is a mathematical problem. It's in the list of 7 problems in mathematics. So for those of you who want to rest for the remaining hour, let me tell you in 1 minute the summary of the lecture. How is it related to these big words in the title? Basically, this is not a physics talk, not an astronomy talk. For me, this night sky will represent a collection not of stars, but of computational problems, which we are studying. And in this collection, there are 2 galaxies. One is called NP, which you should think of as all the problems you would like to solve or understand. And inside it, maybe properly inside it, I should stand maybe, is another collection of problems called P, which is the problems that we can solve. And it turns out that these are not only computational problems out there, there are problems of scientific nature, there are mathematical problems, intellectual problems. And so, given that this is an intuitive explanation of the classes P and NP, to know whether they are equal or not, basically asks what is the limits of what we can understand about problems we want to solve. Okay, so now let's be more specific. That's the plan of the lecture. I will first talk about just computation, how in various forms of it. Then we'll go to algorithms, which are the language we use to understand computation. And then we'll start talking, I'll give you a crash course on computational complexity. I'll talk about efficient algorithms and the class of problems P. I'll talk about efficient verification and the class of problems NP. And then we'll discuss their relationship, and a particular important part of it will be the notion of NP completeness. And then we'll just understand further what are the implications of this question of P versus NP. So computation is, naturally thought of as things that happen in your computers or maybe in your calculators. And what I want to first argue is that you should think of it very broadly and think of it really as like this science without boundaries, something that happens everywhere, in particular in all these fields. So I'll just define roughly computation, will be defining it a little more precisely as any process that we are trying to understand or perform in nature, in life, in everywhere, that happens as an evolution, a process, which somehow transforms one structure into another through simple local steps. Okay? It's certainly what's happening in a computer, but it happens everywhere. And I'll just demonstrate it in a few minutes by a sequence of examples, a variety of examples that I'm sure you're all familiar with. We just stress that each of them has some natural computational component. So, you know, I could have picked any number of examples. These are two examples, maybe physics and biology, of evolutions. It's the evolution of a fetus in the womb, and that's an evolution of the weather. And it's convenient, if you think about computation, to think of the initial data as input and what you want to find out or what happens after a certain amount of time as the output of this process. And actually, there are two computations that happen here. One is what nature performs. It really evolves, you know, this structure to this structure. And the other is about our understanding as scientists. You know, when we have a scientific theory about these processes, we would like to be able to predict what will happen if we have the initial data. So that's computation that we may do by simulations. You know, every process can be understood on many different levels. You know, I don't have H1N1 would be more appropriate for now, but that's from the SARS epidemic a few years ago. You can understand it at the global level, you know, how it infects people around the world. You can understand it at the cellular level. It's the same process on a different scale. And even though, you know, I somehow put arbitrary start times and ending times for the process, of course, they are evolving. And one basic question we want to understand about such processes is what's the limiting behavior of a process? Will it, let's say, an epidemic, will it die out or spread forever, kill us all? There are computations in mathematics, of course. When we have, you know, equations we'd like to solve, we think we are usually given or have to find out this process that will solve them. Proving theorems in mathematics, those of you who are mathematicians here know what I'm talking about. It's definitely a computational process, and the verification of, you know, the proof of the theorem is a computational process, step by step, checking the derivations that they are logically correct. Well, lots of examples if you think just about cognitive processes that happen, you know, emotions or recognition and many more. There are computational processes in, you know, in basically every object that you look about you. So we have really computation everywhere. And the question now I want to talk about is how to describe computation. What's the language to describe a computational process in more detail? And that's the language of algorithms. And before I talk about this, I want to recognize the hero of this, well, this talk and much more. This Alan Turing, as you see, had a very short life with a very tragic end. In 1936, basically his PhD thesis, he wrote a paper with this title, on computable numbers with an application to the unchained loops problem, which is the most important scientific papers in the history of science. I will argue this. In it, he does the following amazing things, and some more. First and foremost, from which everything follows, he gives a formal mathematical definition of an algorithm, okay, which is the most primitive way you can think of, or he imagines a computational process might be. Today we call it a Turing machine. And the first thing it does, which I will not talk about at all, is it really started the computer revolution. From that point on, people started building general purpose computers. In particular, Turing was involved in this project. So everything you use today as a common thing is actually started there. In it, he formulates a thesis together with Church that states that even though his computer is the most primitive thing you can imagine, it can simulate any reasonable process, any natural process, for example. And in it, this computer science started there, but he already puts a limit on what computation can achieve. Not every computational problem can be solved. So that's already in the initial paper. We'll talk about that. So what's an algorithm? I mean, the best, you really all know. The best way is to describe it by example, which we all learn in second grade, which is the algorithm for addition. It's written here in this white rectangle with the red boundary, which I will always use as, to capture algorithms. Here it is, we run it. It basically says that when you add two digital numbers, you just go column by column and add the digits. And the important thing is that the medium in which it happens is just some geometric array of things that have some neighborhood structure. And this, we are allowed to move our focus just to neighboring cells, manipulating only very small finite objects. And that's the general idea. An algorithm is just a step-by-step, local, simple, mechanical procedure like what's written here informally. It can be written mathematically precisely, and for those of you who program, that's just a computer program today. And the important thing is that an algorithm must halt in finite time. So no matter what two decimal numbers you feed it, it should compute their sum and stop in a finite amount of time, and every algorithm should do it. And now the question is, you have a formal definition. I didn't write it down. I wrote an informal definition, but you have a formal definition. And the question is, what can be computed and what cannot be computed by algorithms? Can all computational problems be solved by algorithms? And as I said, well, I want to emphasize here that the algorithm, the description of the process is finite. It's just, some number of characters, 100 characters. But this process, this computer program, is supposed to be able to add numbers of any length, all possible inputs. And already, because you have a formal mathematical definition of an algorithm, of what it means to be able to compute something, you can talk about those problems which are solvable, that have an algorithm, and those problems which are not, and see whether there are any that are not. And in fact, Turing, as I said, already gave the first example, showing that this very basic problem, maybe the most important problem of computer programmers, just checking whether a program has a bug, let's say whether it runs forever sometime, is unsolvable by algorithms. There are basic problems in computer science for computer practice that are unsolvable. It took about 30 or more years to see that there are basic problems in all sciences which are completely unsolvable. Matyasevich showed that the basic problem of solving solutions in equations in integer is unsolvable. There is no algorithm which always decides correctly whether an equation has a solution. Conway showed with this game of life that the problem we talked about before, whether epidemics spread forever or die out, is impossible to solve by algorithms, even if we know precisely the initial data and we know precisely the way the epidemic behaves, the rule in which it behaves. So these are things we'll never understand completely. They are just too hard to solve computationally. What we want to focus in this lecture is on the solvable part. So there are solvable problems, but solvable, as I said, means solvable in finite time, and actually we don't have finite time in our lifetime. We just have short time. And the question is, what can we solve quickly? And that's the subject of computational complexity theory. That's the subject of trying to understand how much resources are needed by a computational process, by an algorithm. So what I'm going to do next is give you the highlights, or at least the highlights I'll need, of computational complexity in order to talk about efficient solvability. So how do we measure the efficiency of an algorithm? So we have an algorithm like the addition algorithm or any algorithm to solve a problem. How do we measure the quality of this algorithm? The way we measure it is by asymptotic analysis. And what do I mean by that? We want to understand how the algorithm behaves, let's say how much time it takes as the data we feed it grows larger and larger. We want to see how it behaves as we feed it larger and larger inputs. So, you know, we measure how long it takes for small inputs, larger inputs, larger inputs, larger inputs. So as examples, you know, if you must be familiar with Rubik's Cubes exist in all sizes. Maybe they are not sold, all of them, but you can imagine. Suppose you have an algorithm to solve them from any starting configuration. You want to check how many steps it takes for 2x2 ones, 3x3 ones, so etc. So you want to understand your quality of your algorithm for larger and larger cubes. Or if you have an algorithm to solve Sudoku puzzles, you know that these are the more familiar ones, but there are also 4x4 ones, 5x5 ones, and you should check your algorithms on larger and larger Sudoku puzzles, how long it takes. Let's see a few examples that are familiar. So we talked about the addition algorithms. The addition algorithms is a particularly simple one to analyze. We saw that it was marching on the column, so it went down 3 steps, went out 3 steps, and then moved to the next column. So, you know, the number of steps it inverses 6 times the length of the data in decimal. So if you are adding n-digit numbers, the time it will run, it will be maybe 6 times n. So that's extremely fast. You may wonder, and you should wonder, and that's the business we are in. When you have an algorithm, can you do better? Is there a faster algorithm? Well, in this case, the answer is obviously no, because basically this algorithm solves the problem as fast as it reads the data, okay, up to some small constant. So that's a really great algorithm. That's the gold standard. If we can have such algorithms for other problems, it would be great. So let's see other problems. Multiplication, maybe that's a 3rd grade example. Certainly you are familiar with this algorithm. I didn't write it down, just wrote down, typical result of multiplying 2 numbers. We get this shape, which is obviously quadratic in size. If the size of the data was n, the number of digits here and the number of operations is about quadratic in n squared. So that's still a very fast algorithm. So you can, for example, multiply numbers of 10,000 digits in a second on your laptop. So it's really fast. Again, we should always ask, is there a faster algorithm? Anybody wants to guess? How many vote yes? How many vote no? You don't want to vote. There's actually a much faster algorithm that you cannot teach in 3rd grade because it's too complicated. But, it's still not as fast as the algorithm for addition. So we don't know if there's an algorithm that's as fast as addition for this problem. Here's another problem, the factoring problem. What's factoring of an integer? Well, here's you can take these 2 numbers and multiply them. You get this result. You can believe me. But the factoring problem is, suppose I gave you the outcome of this multiplication problem and ask you what were the factors. That's seems like a much harder problem. We want to find, I give you this number A, find the factors. Well, there is an algorithm. There's definitely an algorithm. For example, you can try all possible divisors. You try 2, 3, 4, 5, 6, up to, let's say, square root of A will be enough. And it's, certainly a simple algorithm. Let's look at its performance, its running time. Well, if there are n digits, there are possibly 10 to the n numbers, and you have to try square root of them. 10 to the n over 2, that's exponential in the length of the data. That's terrible. If your number is, let's say, 1,000 digits, which is a really tiny number, if you think about data from astrophysics or biology. This is a tiny number. But using this algorithm, this exponential algorithm, the time it will take on the fastest computers will be billions of years. So that's really not practical. Again, you should ask, is there a faster algorithm? That's the simplest. And the answer again is yes, but it's still exponentially slow. So that's not a good one. And actually, we don't know a much better one. So the business we are in computational complexity theory, is just understanding for basic computational problems, do they have an efficient algorithm? Are they easy or don't they? Are they hard? And finding efficient algorithms or proving that they don't exist is the bread and butter of the field. That's what computational, theoretical computer scientists do. Now, we arrived to the definition of the first class I wanted to talk about. This is the class P, which was defined already in the 60s. And that's the class of problems for which we have an efficient algorithm. And efficient for this lecture, and what is usually we use it as, is problems for which we have an algorithm running in polynomial time in the input. Polynomial, I mean something like n or n squared or n cubed. Certainly not exponential, okay? Like addition and multiplication. I want to show you several other interesting problems in this class P. So P is just so you're familiar with the term. P stands for polynomial time, okay? Maybe addition and multiplication is boring. I want to show you algorithms that actually affect your life very much. And to some extent, lots of the technology that you see around you in computing is driven by efficient algorithms. If you allow me a slide of propaganda, even if you don't allow me, I am sure that almost everybody recognizes the people in the first row because they were famous inventors of these gadgets that influence our lives. And I want to argue that these guys did the same. They just invented very important algorithms that are, key to technologies you see around you. Let me tell you very briefly these algorithms just to see what other problems populate the class P. Dijkstra invented one of the earliest algorithms, the algorithm that computes the shortest path between two cities. Let's say here you feed it Delhi and Bangalore, and you run, here's the code for the algorithm. That's all. Algorithms are really typically very small, elegant, sometimes very hard to discover, but very efficient. And once you have such an algorithm, then you power lots of things like, in this case, MapQuest, Google Maps, and much more, because internet routing and network flows and this type of algorithm represents a class called dynamic programming, which solves lots of other problems. So that's a fundamental algorithm. Here's another one. I give you two sequences, a pattern and a text, and I ask you to find the location of the pattern in the text, like these three positions. Again, a very naive, simple-looking algorithm, very ingenious and hard to discover. And this and similar algorithms are behind lots of things you use, from spell checking to text processing, biology applications like the Genome Project, plus, sophisticated versions of it are in these, molecular biology algorithms, web search, and many more, are driven by this. The fast Fourier transform, I'm sure many of you know, converts, well, I won't explain it, converts the sequence of numbers, the signal, to its, trigonometric polynomial form. And this is really behind almost all signal processing applications that you see here and many more, from tomography to faxing to image recognition and so on. And the last I want to mention is error correction, in which you get the data points, let's say, on the plane, and you are trying to find a low-degree polynomial curve that passes through most of them. There are some errors, and you want to, despite the errors, to find such a curve that misses maybe, in this case, just 1 point. And this really amazingly simple-looking algorithm, very ingenious, is behind any form of communication or media that you use today. None of these things would work for you, mobile phones or iPods, if we didn't have this algorithm. Okay, let me go back to the night sky and see where we are. So we identified a galaxy here of problems that we call P, of those, the collection of problems that we have efficient algorithms for. And this class P, as we saw, has many interesting problems and important problems for technology. But what I want to ask now is, does it contain all the interesting problems? Is every problem we want to solve there? So what are interesting problems? Certainly it does not contain all problems. We saw that there are problems that are completely unsolvable. So certainly they are not solvable efficiently. But those are problems we cannot hope to touch. What are the problems that we really can hope to touch but still don't have efficient algorithms for? So in order to understand this, let's restrict ourselves to problems of the search type, when you are searching for something. Almost all problems are like this. So here's a collection of 5 search problems. Some of them we've seen. In fact, all of them we've seen. Shortest path is find the short path between 2 cities. Pattern matching, find the occurrences of a pattern in a big text. Factoring, find the factors of a large number. Theorem proving, I give you a theorem, conjecture like the Riemann hypothesis, very famous in mathematics. Prove it in, some limited space. Sudoku puzzles, another computational problem. You have to find the solution to fill it up. The problems up, we have already seen. They have efficient solutions. The problem below, we suspect they are hard. We still don't know. So what's common to all of them? Well, one thing that's common to all of them is that there are search problems. But I want to go deeper. What's common to all of them? So there's something more that's common to all of them, and very important for the next definition of the class NP. And what's common is that for all of them, both the easy and maybe the hard ones, is that once you get a solution, it's really easy to verify that it's a good one. Okay? Maybe it's hard to find a solution, but once I give you a solution, it's easy to verify. For the top ones, well, they are easy to find, so they are easy to verify, but let's check it for this tree. So for the factoring, if I gave you these 2 numbers, which are supposedly the factors, you should just multiply them out and check. So that's easy. If somebody, like Wiles maybe, proved the Riemann hypothesis, then he would write it down in a paper with lemmas and proofs and the standard mathematical jargon, and then everybody could check it. That's how mathematics works. And certainly with Sudoku, if maybe it's a hard one, but if I fill the numbers out, you can check that it follows the rules of Sudoku. So that's the key thing. All these search problems, if I give you a solution, then it's easy to verify that it's a good one. I have to use my left hand. Maybe I'll move and block the view for some other people. Okay, so problems in NP are problems like find the needle in a haystack. Pictorially, maybe a solution is hard to find, but once you get a solution, you can convince everybody else that it's the right one. In fact, they can convince themselves. The class NP was defined in the early 70s, so this is supposed to be the class of the interesting problems. And now I want to explain that. So first, again, these are the problems which we have efficient algorithms to verify the correctness of solutions, if somebody gave us to them magically. All of them are solvable problems. They are solvable. Why do we know they're solvable? Because for every such problem, if the solution has n digits, we can try all possibilities. You know, maybe it's, you know, exponential in n, doesn't matter, it's finite. And then check for each that the solution, you know, whether it's a good solution or not. So all of them are solvable in principle, in exponential time. And a key question is whether we can do better than this brute force search, whether we can actually solve them in polynomial time. Do they have efficient algorithms? Do all NP problems, all these interesting problems, have efficient algorithms? So we have seen so far, again, we'll keep refining this view of the night sky here. We have added this class NP, which contains the class P, but contains other problems like solving Sudoku puzzles, proving theorems, factoring integers, that we don't know whether they are in P or not right now. But they are all problems for which we have this efficient verification. Okay? And again, just to repeat it, because that's the main point of the talk, the P versus NP, the difference between the two classes is that P are problems for which we have, you know, solutions can be efficiently found. And NP is a class of problems for which solutions can be efficiently verified. The question is whether these two classes are equal or not. So it's a question about what's the relationship between finding and verification. And, you know, at least practice or life teaches us that they are probably not. And the general belief, the conjecture is that they are different. There are some of problems in NP that are not in P. That's the belief. So until now, I talked about computational problems. At least all the examples were sort of computational problems. And I want to convince you now that this question of whether these two classes are equal or not is really a central question, not just of computer science, but also of mathematics and, you know, basically all of science and technology. So how can I do that? Well, let me do a caricature version of the work of mathematicians, scientists, engineers, okay? In a form of, you know, search problems. I think all of us in all these classes are basically solving search problems of various types. Mathematicians, you know, it's really a cartoon, but, you know, you can think of it, a mathematician is given a statement like the Riemann hypothesis, or any one of the clay Millennium problems, and asked to find a proof. It's a search problem. Scientists may be given data of some phenomena, biological, physical, something, and are asked to find a theory that explains it. An engineer is given usually a constraints on various, you know, I don't know, some resources, size, weight, energy, whatever. And it's supposed to find the design for, you know, whatever you think of, bridge, medicine, phone, lots of things. So they are all search problems. And what's common to all these search problems? All these search problems that really we are, you know, in the business of, you know, solving. I claim that for lots of them, this of course, it's a thesis, not a theorem, in many of these intellectual challenges, verifying that the solution we found is good, the theory, the proof, the, you know, the design, verifying it is an easy task. Maybe not finding it, but verifying that what we found is what we were looking for is an easy task. And you know, the convincing argument for that is basically that if it wasn't so, we won't even start looking. If you're searching for something, but you don't think you'll know when you'll recognize it when you find it, you know, you won't even start. So, speaking high level, all these problems are in NP. Now, if P equals NP, then there would, scientists, engineers, and mathematicians would not be needed. We'll feed it to the computer program and find whatever we were looking for. In some sense, it's utopia. It will put out of a job many people. And maybe some intuitive meaning of this P equals NP, and maybe a reason why we don't think it's true, is that it means that in some sense creativity can be efficiently automated. It's some interpretation. Okay, so like I said, we think that P is different than NP. Right now, after 50 years of research, we cannot prove it. So how do we deal with it? How do we argue about which problems might be hard? How do we even identify reasons to think that some problems are hard? So now I want to talk about that. And this is the notion of NP completeness, or universality of problems. So we saw three problems that whose complexity, we don't know whether they are easy or hard. We talked about them. Sudoku solving, theorem proving, and factoring integers. It is an amazing fact for anybody who hasn't seen it before, I think, that these problems that are so different from each other when you first think about them are really very intimately related. So let me tell you how they are related. Assume that you had a good algorithm for Sudoku, something that solves Sudoku in polynomial time efficiently for all sizes. But if you have such a thing, you found a genie that solves lots of other problems. If this problem is easy, then it turns out that proving theorems is easy. And it turns out that factoring is easy. You can use an algorithm for Sudoku to solve the other problems as well, even though they look so different. And the reason for this is Sudoku is one of these problems which is called NP-complete, universal, which means that if you have an efficient algorithm for this one, you have an efficient algorithm for every problem in NP, every problem in NP. That's the word complete there, or universal. And for this reason, you can just, one way to ask the P versus NP question is to say P equals NP exactly if and only if Sudoku has an efficient algorithm. So somehow we reduce this whole question to something that looks for, like a form of entertainment people do on the train rides. Let me repeat this again. NP-complete problems are of the following nature. If one of them is easy, then all of them are easy. If one of them is hard, then all of them are hard. They, rise together or fall together. We know that Sudoku is NP-complete. We know that theorem proving is NP-complete. About integer factoring, we actually don't know. So again, refining, we see that in NP, we already have the class P, which are all the easy problems. And now we have this other class here, NP-complete, which are all the hardest problems in the class. If one is hard, then all of them are hard. So they are the hardest problems in the class. And there are some other problems for which we don't know whether they belong to either class. Okay, so saying that the problem is NP-complete is a way to identify it as a hard problem, short of actually proving that it's hard. We just know that if we could solve it quickly, then we could solve them all. So we have, let's see, I'm doing good, about 20 minutes. Okay, so that's where we are. Let's talk about some interpretations of this situation. I want to just keep it there for another few moments. It's a roller coaster of a talk because there are lots of notions that I introduced here. So where we stand here is that we have this class NP. Inside we have the class P of those problems that we can solve quickly. NP is the problem for which we have efficient verification of solution. We want to know whether P is equal to NP, whether every problem that has efficient verification we can actually find solutions quickly. We argued that NP contains lots of important intellectual problems in all the sciences. And in it, we identified another class of problems. These are the NP-complete problems, which are the hardest in the class. So if we want to know whether P equals NP, all we have to, if we want to prove that P equals NP, all we have to do is give an efficient algorithm for any problem here. If we want to prove that P is different than NP, all we have to do is prove that one problem here is hard. Okay? And a problem is NP-complete means that it's probably really hard. So again, we said it, and we saw some examples of NP-complete problems. And the question is, how special is this phenomena? How rare are NP-complete problems? They look pretty, special in their power. They somehow encode every problem in NP. Well, it turns out that there are thousands of such problems, not only in computer science, but in mathematics, science, biology, physics, economics, every branch of science. In fact, NP-completeness is probably the greatest export of computer science to the rest of the academic community and technological community as well. To see this, you just have to Google. Just Google NP-complete and do it in Google Scholar, which looks at scientific articles containing this phrase. And you'll find that in journals of biology, economics, mathematics, and more, these scientists that are not computer scientists are writing papers proving that problems are NP-complete. Why do they even bother? I mean, why do scientists in these disciplines, in all disciplines, writing papers about problems in their field that they are NP-complete? Well, it turns out that NP-completeness not only captures computational difficulty, but in these other sciences somehow captures some nastiness or lack of structure in a problem. And knowing that a problem is NP-complete in whatever area of science you're in somehow suggests is a potential guide to modeling whatever phenomena or structure you are trying to understand. So let me say a little more about this. I want to somehow talk about taking the axiom P different than NP as a law of nature, much like the second law of thermodynamics. Nobody will imagine building suggesting a physical theory that violates the second law of thermodynamics. So in a similar sense, I want to suggest P different than NP as such a law of nature. So here are a few NP-complete problems in these other disciplines. So for example, in biology, finding a minimum energy configuration, which is protein fault. Well, you probably know that the three-dimensional structure of a protein determines its function, and we'd like to understand, given a sequence of amino acids that describes a protein, how will it fold? What will it fold to? And if you just say your theory is that it folds to the minimum energy configuration, well, you should know that this problem is NP-complete. If you're talking about soap bubbles and you claim that, soap bubbles, relax to a configuration of minimum energy, you should know that this is the problem which is NP-complete. And if you claim that, in economics, that Nash equilibrium or market prices, are the rational solution, they arise in market economics, you should know that this problem is, well, sort of NP-complete. So what does it mean? Well, if that's your theory or your model, you are somehow claiming that nature or market or people efficiently solve NP-complete problems. There are three possibilities, I think. One is that the model is wrong. Another is that the inputs that actually are being solved by these processes, let's say the proteins which fall to minimum energy, are very special. Maybe they have evolved, 2 billion years, so that the solution to their minimum energy configuration is efficient. Maybe we can, NP completeness just says that, there are some inputs for which it may run exponential time, but maybe the proteins in our body fold, very efficiently. So nature can solve its folding problem. And the third possibility is, which we actually made sure doesn't happen, is that P equals NP. If we believe that P, those problems solvable in polynomial time on a computer, actually capture what can be solved efficiently by nature. So that's the next thing we need to understand. What is the, levels or from DNA molecules or from electrical circuits that will, create faster algorithms? So the question is whether nature can do things faster than a computer does. And faster, more than polynomial speed up. And you can try also every process in nature. You can enhance it to, connect it to your computer. Let me talk about two general phenomena that nature provides and may aid computation, deterministic computation. One is randomness. There are lots of sort of unpredictable phenomena in weather is a good example, or radioactive decay, or lots of other processes that seem to have an inherent entropy in them. And we may try to harness them and look at algorithms that use random coins. Or, using quantum mechanics, it's even more elaborate, and I won't get into this, form of randomness. It's actually allowing interference. And you can ask whether, adding this or adding this increases computational power, is better than just deterministic polynomial time. But it turns out the first one we understand pretty well, at least to the extent that if we believe P is different than NP, it's a remarkable connection, but it turns out that if P is different than NP, or stronger statements of this form imply that randomness will never adds power to this, to standard computation. Randomness is useless in enhancing computation, by more than polynomial factors. On the other hand, with quantum mechanics, if we could really enhance it into our computers, so there are big projects, probably many of you know, are aware of them, to build quantum computers based on quantum mechanics, then we would be able to do more than we can do today. In particular, we would be able to factor integers efficiently. So there is a quantum mechanical algorithm to do it, only the machine is not there yet. Okay. We talked about, we said that P equal NP will solve maybe all the problems we want, and that will be great, but we don't believe it. So we sort of think that P is different than NP. What is harder, addition or multiplication? Everybody answers multiplication. And you ask why? Well, they say, well, we learn in second grade, this we learn in third grade. And in fact, it's sort of a good answer. But these are only the algorithms we know. It's quite possible that somebody tomorrow will discover a much better algorithm for multiplication. As I mentioned, there is a better algorithm for multiplication than the third grade one. It uses fast Fourier transform, and it works almost in linear time. And it's quite close to the time of addition, but not quite. But it's really possible that they are equivalent. It's really possible that someone tomorrow will come up with an ingenious algorithm that in linear time, in the same time as addition, solves multiplication. It's really possible. And in fact, on a particular data representation, it is possible. Not the one, not the decimal one, but another one. So it may be that the two problems are exactly equivalent in difficulty. We just don't know.
Given recent research, some people have made the suggestion that the brain is a working quantum computer. So wouldn't that imply that as far as the mind is concerned, P is equal to NP?
Well, I think that we are very far from understanding the brain. It certainly, to me, is a physical system which may employ quantum mechanics. Why not? I don't know. But we don't know the power of quantum mechanics. Even in the theoretical side, we know that quantum algorithms can solve factoring, but we don't know that they can do Sudoku. So we don't know if they can solve NP-complete problems. So forget the brain, even the theoretical one, the theoretical model of quantum algorithms may not be able to solve NP-complete problems efficiently.
So you have told that there is this NP-complete problems and P problems, and you have told that this factoring, we don't know whether it's falls in NP or P, NP-complete or P. But my question is there any problem that you know that is in NP but doesn't fall under P and NP-complete?
Yes, it's a very good question. And you notice that if we knew such a problem, we would know that P is different than NP, right? So if we knew a problem that is neither in P nor NP complete, we would know that these two classes are different. So we don't know such a problem. What we do know is that if P is indeed different than NP, then there are problems which are neither this or that. Yes.
I have one question. Suppose we find the limit of the power of computing any problem. Say we suppose that's the final place we can go to get the answer. So can we say that that is some implication of the solution we can expect?
I'm not sure I understood. What? Okay, can you repeat it maybe in different words?
We can go, say, suppose we can go up to a certain limit to solve any problem. So can we indirectly infer that it indicates the sort of solution we may expect?
Yeah, so I think I understood. So let me just interpret. The question is, suppose we could just run for so much time. Can we actually check whether, let's say, P is different than NP? Yeah, maybe we try with all our computer powers to solve, the theorem proving problem or the Sudoku problem, and just try to guess from this, just compute the optimal time it takes for size 2, 3, 10, 100. Can we see whether the curve is exponential or polynomial? That was your question. No, because it's quite possible that you have a polynomial time solution with a big constant in front of it. So maybe it takes, 10 million times n squared. And then, because that's actually a good point, and it's the disadvantage of asymptotic analysis, that we get an asymptotic behavior that looks like efficient, but sometimes, it's an overuse of this word efficient. In fact, when you look for real good algorithms like the few ones I demonstrated, they are not only good asymptotically, but the constants, are really, small. So they are really efficient in practice. So the connection between the theory and practice is an important one that I didn't elaborate on.
Excuse me, I have one last question.
Actually, sorry, where are you?
I'm here. Here to your I'm to your right. Here.
Okay.
Yeah, my question is more on the informal definition of the algorithm. You named it, you called it a step-by-step, local, simple, and a mechanical procedure. I want you to focus on the word local. When you said local, did you mean local in space and time? When you use an algorithm has to be causal. It can't be non-causal, as in you cannot use information that will be provided in say, the future. So an algorithm would typically be an iterative step, or your next step would build on the information that you have right now, which means the word local would imply that the information is available locally in space and time. Now, local in physics would imply that you have energy, entropy, as well as physical bounds on the system that you're talking of. Now, what if the problem is intrinsically non-local? Then the information cannot be localized, and the whole concept of coming up with an algorithm to solve a non-local problem would be nonsensical, right?
So you are definitely right. The first part of your question, if I understood it correctly, is which is stating how an algorithm is defined and works, is indeed, it is a step-by-step, it's a sequence of steps which are each local and simple, like the example of addition. Okay, that's how algorithms work, that's how all computers work. They, evolve information which is present by doing local operations. What is local operations? Whether they are bit operations or word operations.
Yeah, but you have things like quantum entanglement where you have apparent non-locality.
No,
You have action at a distance.
The locality is not, if you work on a system of n particles, okay, whether, even if they are arranged on a line, you can think of one operation occurring on all of them, or you can think of just a sequence of, gates that act on adjacent ones, let's say pairs. The difference between these two will be just a factor n. This is not going to affect the definition of efficiency. So there is no problem of locality there, no problem at all. If you are interested in efficiency up to polynomial, that has no impact. This issue of locality has no impact whatsoever.
I'm afraid we are running out of time, but there is tea outside, and let's thank the speaker again.
It's fun so much. I love to.